There we go. Compare what you got with what I got. Let me know if there's a difference or if we can correct things. Comments, questions, concerns. Here's the bottom. Comments, questions, concerns. Okay, hearing nothing. Here's questions 5 through 8. 5, 6, 7, and 8. There we go. Okay, flipping, going, comments, questions, concerns, going once, twice. Vikram's not paying attention, sold. 9 through 12, here they are. What can I do to assist you? Maximum compression should be this guy here. Potential energy is there, and 43.8 meters. Bless you. Comments, questions, concerns. Up to 12. Going once, twice, thrice, sold. Here's hoping you actually did your homework. And here's 13A and B. Graph should look like this. Are there any comments, questions, concerns? Harbir and Vikram, or Harbir and Imparis? You're not even looking, comparing your work with my work. Maybe it means you didn't do your work. If there's nothing to compare. Okay. Well, we will find out when you are assessed shortly. Okay. So there you go. Are there any questions anyone would like me to go over from the homework I assigned? Going once, twice, thrice, sold. Okay, today we're going to look at something called nuclear decay. And you guys are going to do some balancing for me. It's going to be great. This might actually be the last lesson, too. Oh, no, this is not the last lesson. Soon. Okay, here we go. Nuclear decay. We'll look at nuclear energy after this. So we looked at gravitational potential, we've looked at kinetic, we've looked at spring potential, and now let's look at, it's going to feel kind of out of place, but this is a good place to look at this section. Now, in the old curriculum, this was its own chapter on radiation, radioactivity, but in the new curriculum, they've put it in here. Nuclear decay. So recall, if you will, atoms have 3 subatomic particles: protons, neutrons, and electrons. What can you tell me about the protons, neutrons, and electrons? Sorry? Anything you can remember about any of these 3? Yes, protons are positive, neutrons are neutral, and electrons are negative. And neutrons have 0 charge. What else can you tell me about these things? What do you remember? Sorry? Okay, these are equal in an atom, and they are different in an ion. That's what makes an ion an ion. Cool. What else do you know about, what else can you remember about protons, neutrons, and electrons? Sorry, Dennis? Oh, we can't read that. This says different in an ion, equal in an atom.
Electrons are like...
Yeah, so these are in, there's an outer shell. 4 electrons. Where are the protons and neutrons both located? In the nucleus. Cool. What else can you tell me? There's one more piece of information that we looked at when we did this back in chemistry. What one more piece of information can you tell me about protons, neutrons, and electrons? Which two of these particles contribute to the mass of an atom? Neutron, which two? Protons and neutrons. All the mass, all the meaningful mass is found here in the protons and the neutrons. Most of an atom's mass is found in the protons and neutrons. Specifically, if you add these two numbers together, if you take your protons, P plus, and you add them to the neutrons, N0, you add those numbers together, you get the atomic mass. Electrons weigh so little, we don't actually even care about them as far as the mass is concerned. Okay, so recall. When atoms gain or lose electrons, we call them ions. This is not a recall, this is brand new. You can lose more than just electrons. The one thing you cannot lose is a proton. The proton defines what kind of element you have. The proton is the atomic number, it doesn't go anywhere. But you can gain or lose neutrons. The neutrons are allowed to change. And so the atomic number will stay the same. Carbon has an atomic number of, what is that? 1, 2, 3, 4, 5, 6. So there will always be 6 protons in carbon. But the neutrons are allowed to change, and we have a name for this. When the electrons change, we call them ions. When the neutrons change, we call them isotopes. And we write these things a little bit differently. When we're talking about these things now in nuclear chemistry as opposed to classical chemistry, we're going to write them like this. So if I want a hydrogen atom, a hydrogen is there. Hydrogen, if you look at the periodic table, I gave you a periodic table on the inside front cover. Hydrogen has a mass of 1 and an atomic number of 1. Atomic number is up in the top left. Mass is, mass is down here at the bottom. Atomic number, mass. So hydrogen has an atomic mass of 1 and an atomic number of 1. So that means we throw a 1 there and a 1 there. This guy down here is the atomic number. This guy right here is the atomic mass. The atomic mass is the protons plus neutrons, and the atomic number is the protons. So what can you tell me about the number of neutrons in a hydrogen atom? There's 0. Because the mass and the atomic number are both 1, that means there's 1 proton, no neutrons. So this thing has 1p, 0 neutrons. But you're allowed to change the number of neutrons, and sometimes in the environment, this change will happen on its own. So if you go out into the environment and you find something with 1 proton, but it has a couple neutrons, it's still hydrogen, it's just what we call a different isotope of hydrogen. So an example of this would be something like this guy here. If I had H3, 1, this is still atomic mass, this is still atomic number. The number of protons hasn't changed. There's still one proton. But what has changed about this hydrogen? We're not, no, Malik, we're not speaking to neutrons. Dennis, you were going to say? What did you just say, Dennis? The neutrons are different. How many neutrons does this thing have? 2. So it's the same atom, it's just heavier. It's got 2 neutrons as a part of the atomic nucleus. It's always, so mass minus number, atomic number, will give you the number of neutrons. And so we name these things different ways. We would call this guy over here hydrogen 1, hydrogen dash 1. And this guy over here we would call hydrogen 3. Different isotopes of the same element get their mass added on at the end. A common one is another example. We'll talk about these 3 in a second, but another example we talk about is carbon. Hands up if you ever heard of carbon dating, like radioactive dating. Okay, carbon dating. What carbon dating is looking for is something called carbon-14. Carbon normally has a mass, like nowadays, if you go and look at your standard carbon sample, it will have a mix of different isotopes. It might have carbon-13, it might have carbon-14, it might have carbon-12. Carbon-12 is what we typically assume carbon is going to be. This is what it'll say on the periodic table. But there will be a percentage of the carbon in the sample that's carbon-13 and a percentage of the sample that's carbon-14. And we know at what rate these two turn into this one, which is what we're going to talk about today. We're going to talk about something called nuclear decay. The higher isotopes will decay into lower isotopes. And so we know how fast this happens. And so we can say, okay, well, there should be, if this carbon sample was taken from today, we know there would be this much carbon-14, but it's missing some. And so because there is less carbon-14, we know this thing needs to be older than today. And so we can go back and we can make an approximate guess as to the age of the material based on how much carbon-14 is missing. Yes, in parts.
So how many neutrons can have the upper on mass?
Technically, the lower end would be 0 and there is no upper bound. Like, practically that's not going to happen because the more you have, the less stable you are. That's the whole premise behind nuclear decay, is if you are inherently unstable, it's not going to exist for very long. But in the lab, you can force things. You could, like if you went into the lab, we could force a sample of carbon to have tons of neutrons. As soon as we let the thing go, it'll decay into nothing.
There's a lot of conditions you need to get more neutrons.
High energies. And everything to a degree is has a inherent instability to it, and things will decay over time. Just the more stable they are, the longer they take. So other examples are things like cobalt-60. Cobalt comes in a bunch of different forms, and if you look at the periodic table, cobalt is, where's cobalt? Cobalt is CO. Where are you, cobalt? Beside which? There it is. So cobalt, if we go by what I told you to do back in chemistry, we just took the atomic mass and rounded it up. So that would be cobalt will have an atomic mass of 59. Cobalt-60 has one more neutron, and cobalt-60 is the radioactive material that we use in radiation therapy to kill cancer. Like my mom had breast cancer a few years ago. She didn't have to have chemotherapy, which is a drug. She had radiation therapy, which is using targeted radiation samples to effectively kill these cancer cells. And so one of the isotopes we use is cobalt-60, radioactive. Iodine-131 we use as a tracer. So different types of cells absorb iodine at different rates. If we make the sample of iodine radioactive, if you recall, iodine should have a mass of 127. We take that 126.9, we round it to 127. If you jack the number of neutrons up to or the mass up to 131 by adding 4 neutrons to it, now you get a radioactive substance that you can trace. And so they inject the body with iodine 131, and different kinds of cells absorb iodine at different rates. Cancer cells will absorb iodine at a higher rate, so you'll get the concentration of iodine, and then you can find where it is in the body by looking for the radiation, the radioactivity that's present. And then there's something called tritium. Tritium is hydrogen with 2 neutrons, so this guy right here is tritium. And tritium is a form of hydrogen that glows in the dark, which is a little bit weird to think about. Tritium is used in nuclear reactors. For things. So let's fill in some of the blanks here, stuff I've talked about already. If isotopes have too many neutrons compared to protons, they have too much energy. The more neutrons they have, the more energetic they are. They are inherently unstable. Things do not want to be unstable. They want to reach a degree of stability. And to reach stability, they need to give up. They need to get rid of the extra energy, and they do that in 3 different ways. There's 3 different types of radioactive decay that we're going to look at, or ways that atoms get rid of the energy that they have. The extra energy that is released from isotopes is transferred through radiation, and radiation is a way energy is transferred in the form of electromagnetic waves and other things, and some particles, because it's not all electromagnetic waves, as you will see. Okay, so nuclear decay. Nuclear decay is how this happens. Nuclear decay is the change to an atom due to the emission of particles or energy. It is a way of high energy isotopes to release their energy and become more stable. And we're going to look at 3 kinds, something called alpha decay, beta decay, and gamma decay, which just so happens to be the first 3 letters in the Greek alphabet, alpha, beta, gamma. And so they didn't have a fun way of saying, oh, this is decay number 1, this is decay number 2, this is decay number 3. And so that's effectively what they've done here with alpha, beta, and gamma, just the first 3 letters of the Greek alphabet. When you're ready, flip the page. Isotopes. Okay, so here's alpha decay. So just so we're clear on when this happened, once you're done that, you can throw that in the garbage. Okay, so alpha decay. Alpha decay, they're named like this because alpha was the first one discovered. Alpha decay was discovered in 1899 by a chemist that you should be familiar with, a chemist that you would have looked at in Science 9 by the name of Ernest Rutherford. Don't you dare say no clue. How dare you say no clue? You guys would have looked at different forms of the model of the atom back in middle school or grade 9. Like there's the plum pudding model for the atomic structure. No, this is not ringing any bells. Atomic models. Dennis never saw this. Himparis, did you say yes? You remember this? Okay. At some point in your educational past, you looked at atomic models. and our understanding of what an atom is. Rutherford was one of the last guys to put his, basically went Rutherford then Bohr, were the guys who kind of finished up what the atom looks like. And so Rutherford actually used something called alpha decay to figure out what the atomic structure of gold looked like. You may have heard of, well, you would have at some point learned about his experiment. He shot alpha particles at a sheet of gold foil. This is ringing any bells. Those particles that he was shooting, those alpha particles, are alpha decay. What we have since discovered is that an alpha particle has 2 neutrons and 2 protons. If you look at something that has 2 protons, what is that on your periodic table? What's atomic number 2? There's 2 periodic tables up on the wall right behind you. It's helium. So an alpha particle, 2 protons, is helium. If you look back at the periodic table on your inside front cover, helium has a mass of 4. And what he discovered was that in alpha decay, what's being omitted is functionally a helium atom. The alpha particle has a mass of 4. Helium has the atomic number 2. So this thing is your 2 neutrons, 2 protons. These 2 added together give you the mass, and that gives you the atomic. That shouldn't be number 2. That should be the hashtag. My bad. So what happens when alpha decay occurs is that helium is spontaneously created out of whatever is decaying, which is weird to think about. Alpha particles have the same number of protons and neutrons as helium. Is the blank right there. So sometimes they're shown as helium because they are. When an isotope releases energy by emitting alpha particles, the isotope releases, whatever it is, releases a little bundle of 2 neutrons and 2 protons. And so then as a result, the isotope, whatever was sitting there, released 2 protons and 2 neutrons. So for the isotope to lose 2 protons, what happened to the isotope? If protons left, 2 of them left, what's the first thing that happens to the isotope, whatever it is? If protons are disappearing, what number is changing of the atom? The element's changing, yeah. The element has to change because your atomic number dropped too. The atomic number goes down too. So an example of this that I have is this guy right here. So radium-226. This particular radium has a mass of 226. The atomic number of radium is number 88. This thing is inherently unstable and as such is radioactive. When it decays, it releases an alpha particle. This is your alpha particle. The Greek letter alpha looks like a fish. And so because the 2 protons have left, the atomic number of this thing drops too. Well, radium has an atomic number of 88. If it loses 2 protons, it goes down to 86. Now it's no longer radium, it's radon. It's a different element entirely. And not only that, because it loses 2 protons and 2 neutrons, the atomic mass drops 4. Goes down 4. So you had radon with a mass of 226, and now radium with a mass of 226, and now you've got radon with a mass of 222. Because you lost 2 protons, 2 neutrons. So this is where the balancing that we're going to look at is going to come in. This guy here, the 226, you took away 4 to get from one to the other because the mass dropped 4. And to get from here to here, you took away 2 because there were two protons that left. So I've got uranium. Uranium is U. Uranium-233 is the name of the sample because that's its mass. When uranium gives up an alpha particle, it becomes something called thorium. Michael and Elijah, wake up. To get from 233 to 229, what happened? How much mass was lost? 4. So all that mass needs to show up over here. To get from 92 down to 90, 2 protons had to be disappeared. This is another one. Pu is that plutonium? Pu is plutonium. This is plutonium-239. When plutonium undergoes alpha decay, becomes uranium. So alpha is the easy one to label. An alpha particle is always 2 and 4. So then what is the mass and atomic number of the uranium that's left over here? Well, plutonium is 94. It lost 2, so uranium's got to be 92. The atomic numbers on the right-hand side need to add, and the masses need to add. So what does the mass have to be of the uranium that was left over after plutonium decayed? Should be 235. Malik, wake up. Because it was 239. Malik, wake up. And 4 left with the alpha particle. Yes, Imparis. Because you're allowed to, like that's because of this. You're allowed to have, all of these different isotopes are allowed to exist. Sometimes when you decay, you're still radioactive. So now maybe uranium-235, this thing might decay again. And in fact it does. I'll show you what it decays down into. U-235 decay chain. Okay, so here's what happens after uranium-235. Uranium-235, if you want the decay for this guy's going to decay again and release another alpha particle. That's going to be a 2 and a 4. So after uranium is decayed, what's going to be next? Well, 235 minus 4 is 231. And 92 minus 2 is 90. And 90 is thorium. And so what you're going to get here is you're going to get a different element again. Plutonium becomes uranium. Uranium decays again, becomes thorium. And actually, the decay chain is actually really quite long. I'll read it to you. Uranium-235 becomes thorium-231. Thorium-231 becomes protactinum. Protactinum becomes actinum. Actinum becomes thorium again. Thorium becomes radium. Radium becomes francium. Francium becomes astatine. Astatine becomes polonium. Thallium becomes lead. Oh, nope. Thallium becomes lead. And lead is stable, so it stops at lead. Yes, you may. And this rate of decay is millions of years long. That's alpha decay. Questions, comments, concerns about alpha decay. It is the emission of an alpha particle. Flip the page when you're ready. We'll go through all 3 kinds of decay, and then you guys will have a chance to play with them. Here's the next one. The one that comes out after alpha is beta. And beta decay, also discovered in 1899, also discovered by Ernest Rutherford. And it's a different form of decay. Instead of releasing an alpha particle, sometimes radioactive decay looks like this. Isotopes can release their energy by emitting what's called a beta particle. A beta particle is a fast-moving electron. And this is not the same as becoming an ion. Because becoming an ion means losing an electron too. Look at what happens here. In beta decay, a neutron in the nucleus of an atom turns into a proton and an electron. This is weird. The neutron in the atom spontaneously turns into a proton and shoots out an electron. Electrons have no mass. But have a atomic number of -1. Oh, you're awake. Never mind, we're good. So here's what beta decay looks like. If I have lithium, lithium has an atomic mass of 8 and an atomic number of 3. If lithium undergoes beta decay, the atomic number -1 pops out. And in order for it to be balanced, these two numbers have to add up to what we started with. They have to be balanced, just like balancing chemical equations. Please put your phones away. None of you need to be on them right now. So if this was a 3 and -1 shot out, that means the atomic number must jump up to 4 because 4 plus -1 is 3. And the mass remains the same because there's no mass that leaves with an electron. No mass has left. So these two masses must remain the same. So when beta decay happens, this is what you're going to get. Lithium turns into beryllium, the atomic number goes up 1, and an electron shoots off. And because that electron is fast moving, it's carrying a whole bunch of kinetic energy with it. So a couple examples. Here is the decay of carbon-14. Carbon-14 goes through beta decay. So if you look at what's happening here, no mass was carried away, so these two remained the same. If you had a 6 and -1 was taken away, what's the atomic number of what needs to go right here? Nope. 7. Because 7 minus 1 is 6. -1 was taken away, so it's going to go up 1. These two numbers need to add to give you that guy there. Okay, so you got tritium. Hydrogen 2 is what this is, also called tritium. It undergoes beta decay. Beta is always -1. So what plus -1 is going to give you 1? What goes here? It's 2. So that must mean this particle is helium, because it has 2 protons. Yes, Malik. No, because 2 minus 1 is 1. These two atomic numbers have to combine to give you the atomic number you started with. Yeah, do what you gotta do. Yeah. Okay. And then the last one is this guy down here, Tc, technetium, undergoes beta decay as well. What are the numbers that go here on something called Rutherfordium? It's going to be 99 and 44. You bet. Okay, so now that we've done, here, I'll take a picture of this so I can make sure I get it right. Now that we've done alpha and beta decay, I can show you what happens to uranium. Because it's a combination of these two things. Okay, here we go. You don't need to write this down, just experience it with me here in all of its glory. Hey, Luca, how'd that math test go on Friday? How'd that math test go on Friday? Nice. Okay, so we start with uranium. Uranium 235, and uranium has an atomic number of, dang, what's uranium's atomic number? Uranium's atomic number is 238. Nope, that's the mass. 92. Okay, here we go. So, uranium-235 is the kind of uranium found in nuclear reactors and in nuclear weapons. It is radioactive because it's inherently unstable. Uranium goes through alpha decay and turns into thorium. So, goes and releases an alpha particle. So thorium has an atomic number of 90, and this thing has a mass of 231. This thing is still inherently unstable. So what thorium does is thorium undergoes beta decay. Thorium releases an electron. Yes? You're doing it, okay? And becomes something with a, what's the atomic number that needs to go here? Careful. If this is -1, this needs to be 91. So what is atomic number 91? You got your table in front of you. What's atomic number 91? PA. Protactinum. Protactium? Protactinum. And this thing has a mass of 231. The mass of the thorium and the mass of the protactinum are the same, but this thing gave up one of the neutrons in here became a proton and a beta particle was emitted. Protactinum still unstable. It undergoes alpha decay. So we're going to have 2, 4, and alpha, which means protactinum is going to gain, sorry, no, it's going to lose 2 protons, going down to 89. What's atomic number 89? AC, actinum. And the atomic number is going to go from 231 down to 227. Or the atomic mass is going to become 227. Actinum, still radioactive. So actinum, just because my back's turned doesn't mean you should be on your phone now. Actinum's going to undergo beta again. So beta particle, -1 and 0. This should have actually been a beta particle. Okay, what does actinum become? Actinum goes back up to, if that was an 89, goes up to -1, which means this needs to be 90. The mass doesn't change, 227. Oh look, we've already had 90 in the chain. That's thorium. So uranium became thorium, became protactinum, became actinum, becomes thorium again, but with a different mass. So now thorium undergoes, where is it? Thorium undergoes alpha decay, which means thorium is going to go down to 88. What's atomic number 88? Radium, good. And the mass is going to go down to 223. And this keeps happening. It keeps bouncing back and forth between alpha decay and beta decay until eventually it gets down to, we're going to dot, dot, dot. The final result is Pb with a mass of 207. So over the course of the decay chain, different kinds of radiation are being emitted. Sometimes it's alpha. Which class are you supposed to be in? What class are you supposed to be in? And go into math. Whose math class are you supposed to be in? Who? Sweet, go to math. It's hiding against the wall next to it. I lost it. That's the part of the decay chain of what's going on. So you have alpha decay, we've got beta decay. And there's one more. When you're ready, flip the page. This is the scary one. This last one is called gamma decay. And gamma decay this guy was discovered in 1900 by a guy named Paul Villard. And it was actually named in 1903. So, after alpha decay and beta decay, a nucleus is often left in an excited state which is unstable. To become stable, the nucleus releases a high energy photon, which is weird. It just lets go of light. Photon is light. And it's high energy light in the form of a gamma ray. Now, I showed you this poster before, but I'm going to reference it again. The poster on the wall behind Michael and Elijah is my electromagnetic spectrum poster. And it's arranged by energy. Visible light is right here. So on this chart, this is all your low energy stuff. Microwaves are down here. Wi-Fi is down here. The infrared and thermals right here. This is what you guys are emitting, just sitting here sweating because my class is 24 degrees. This is the visible spectrum. This is the light that we can see. Then you get to UV, then you get to X-ray, then you get to gamma ray. There is nothing beyond gamma ray. Gamma ray is the highest form of energy that we know of, and it only gets more gamma E the higher you go. Gamma rays typically.
There's nothing like we don't find anything.
There's nothing beyond gamma. It's all just degrees of intensity. It's just really strong gamma or weaker gamma.
What do they use that for?
They don't use it for anything. We guard against it. Gamma radiation is what made the Hulk, but in practical terms, gamma radiation kills you. No, we've defined it, I mean, because all of it's the same particle. So, like that poster, just so we're really clear, that poster is all just light. It's the same particle, it's called a photon. If it's a low energy photon, it's lower down on the spectrum. If it's a high energy photon, it's higher up on the spectrum, but it's all just photons. So we just define particular energy bands to have different names. Visible light, UV, X-ray, gamma ray. And so it's because it's not a different particle, it's all the same particle. It just has a numerical energy, like a number difference. There's no reason to call it anything different. Gamma starts here and is anything energy level above this. We have defined to be gamma radiation. Imporus, was that a hand?
Okay, so like, what phenomenon like produces gamma radiation?
It's a great question. Supernova, atomic bombs.
So like, what do they have in common? Makes gamma radiation. It's like
Massive amounts of energy being released. So, like it happens during radioactive decay as well. Like the example that I have here is sometimes you get during radioactive decay, you get an atom that it's content to stay the atom that it is. It just needs to let go of some energy. And so all it does is it just kind of like drops from a high energy state to a low energy state. Kind of when you sit in the chair at the end of a day, you're like, you've had all this stress built up over the course of your day. Your science teacher was an ass and gave you 90 questions of homework, and your math teacher sucked and gave you 50 questions worth of homework, and you finally get it all done, and you're just like, That's effectively what gamma radiation is. It's these atoms, and they just kind of go, except when they do that, they release a high energy photon, a blast of light that is high energy. Gamma has no mass, gamma has no atomic number, it just sits. Yeah? Yes. If a close enough star happened to go supernova pointed in the right direction, or if, sorry, I shouldn't say it that way. If a neutron star happened to spin in the right direction, neutron stars spin so fast, they're emitting gamma rays. If it happened to spin in the right direction, a gamma ray burst could wipe out life on this planet. Yes, that is a possibility. Hasn't happened, obviously, but it could. Gemini. Yes, Malik. Unrelated. I don't know. It's all highly theoretical at this point. Luca. Yes. Yes, but if it happened now, it's not going to hit us for several years. Maybe even thousands or millions of years. Because, I mean, the things that cause these things are far, far, far away. If we got hit with a gamma ray blast today, if in 10 minutes this happened and wiped out life on our planet, that gamma ray burst probably occurred millions of years ago and just took time to get here. It's like a tsunami. An earthquake in Japan takes time for the tsunami wave to hit Vancouver Island. The tsunami that hits Vancouver Island, the earthquake probably happened 2 or 3 hours ago, maybe 12 hours ago. The thing that caused the gamma ray blast to wipe out life on our planet, if it's going to hit us, has already happened. Nope, because when we see it, it's here. Because it's light. Like, that is the only thing. If they see it, that means the light has reached us and we're cooked. Literally. Like, I'm not even using it in your slang. In Paris, we are literally cooked because it would vaporize life on our planet. We would all experience it for the first time at the same time, and you wouldn't even know it hit you. We would all, as a human race, immediately experience whatever the afterlife actually is. We'd all get there together because it would end. That is a planet-ending disaster, and there's no way to predict it. No, because everything's gone. Everything organic would be gone. Depends on your view of the origin of organic life on our planet. But this is an entirely different phenomenon. We're getting vaporized. An asteroid hitting our planet is not a vaporization event. There's still life on the planet. A gamma ray blast, gamma rays would erase life on the planet. All life of every form would be gone. It's that degree of intense. Lemise, you may. Okay, so let's talk about, and gamma decay it's easy to do. Nothing happens. Gamma rays have 0 atomic mass and 0 atomic number. Nothing changes. The only difference here is that the high energy particle has a little asterisk next to it. Yes?
Would the gamma ray definitely atmosphere as well?
Probably. Probably. I cannot answer. But it could. Well, if it hits the sun, it's going to hit us too. Like, if it's going to hit our solar system, it's going to hit our solar system. Nothing. There's nothing to happen on the sun. Like, the sun would just continue to be. I mean, this. I don't think anything would change. Its particles would become highly energized and then release that energy. The sun is undergoing nuclear fusion. We're going to talk about different kinds of nuclear reactions. The sun is constantly undergoing nuclear fusion. Not much is going to change that until it burns itself out. At which point, it's going to vaporize our planet. Because when our sun is finished nuclear fusion, it's going to expand. And it's going to expand to almost Jupiter, which means Earth and Mars are toast. Well, so are Mercury and Venus. We don't care about Mercury and Venus. Emparis.
So how big does the sun need to be to go supernova?
Our sun is too small to go supernova.
Like, so how big would
It will go nova. Is that right? Our sun will nova, but it will not supernova.
think of this cloud.
I'm not going to teach you astronomy, so we're not going to get there. Sorry. Our sun is not, I don't believe our sun is big enough to supernova. Okay. So, I mean, in practice, gamma decay is easy. There's zeros for mass and number. So nothing changes. Magnesium star just becomes magnesium. Iron star just becomes iron. The numbers all stay the same. The asterisk is the only thing that disappears. So in summary, this is what we've got here. We've got alpha decay, beta decay, and gamma decay. And as you can see, as we go along, the particles are getting smaller and smaller and smaller. We went from a helium nucleus to an electron. And then from an electron, we went down to a photon. Yar, wake up. So if we had a sample, let's say we've got a sample over here, whatever this is, some rock. And if this rock was emitting these different kinds of, let's get some different colors here. If this rock was emitting different kinds of radiation, alpha, beta, or gamma, there's going to be different kinds of things that we can use to block this. We want to shield ourselves from radiation, certain kinds of radiation, because not all radiation is bad. You guys have Wi-Fi radiation traveling through you all the time. Hasn't killed anybody yet. Yet being the operative word, yes. But these guys are where things start to get scary. Alpha, beta, and gamma are concerning types of radiation. But fortunately, alpha particles, this guy up here, the green one that I've drawn, that's alpha. Alpha can be blocked by a piece of paper. A singular piece of paper will stop a helium nucleus, an alpha particle. To block a beta particle, an example of something that was, so this is paper. Paper would block this. The next one, let's use no, let's not use purple. Let's use light gray for reasons. An aluminum sheet. A sheet of aluminum would block, this is beta. Now, metal is packed more tightly than paper is. You need those tightly packed atoms to block the electrons that are the beta particles. Now, if you want to block gamma, you need something a little bit more intense. That's the symbol gamma, Greek letter. You need lead. Heavy, heavy metal. Which is why when you go to the dentist and it's time for your x-rays, they put you in a lead vest. Because it's this high, high energy radiation that they're trying to block. And x-rays are just a step down from a gamma ray. Theoretically, yes.
All right, can we try that?
How? So here's what I'd like you to do. You have a whole host of practice questions. This page and the next. I would like, it's a summary of what we've looked at. I'd like you to look at the nuclear decay kinds of questions. And then tomorrow we will look at nuclear energy. There you go. See what you can do with this. You're identifying alpha and beta and gamma decay, and then you're using them to write out the nuclear reaction equations. Yes, Luca? You may. You have your task on your market set giver.